Hello and welcome to the first of likely many videos that we're going to be using, I guess I'll be making and hopefully you'll be using, to enjoy the rest of our semester together for our class in Discrete Mathematics. So this video here is going to be hopefully shorter than most. I do want to take care of some sort of housekeeping business that doesn't have much to do with math right off the bat, and that's just sort of addressing the elephant in the room, the fact that we're even having to switch to an online learning environment, that is you guys using videos instead of coming to class as the biggest change, in the middle or towards the end of our semester. So given that gigantic disruption and all the many things I'm sure everybody has going on in their lives as a result, I wanted to take this opportunity to just jot down a few things that will be changing about the rest of our course. So changes for our class, and I'm going to keep slipping up and saying that these are changes for the rest of the semester. I really don't know that. These are changes for the time being. Right now, I think our university's official policy is these are changes for this current week of classes and maybe the next after that. But who knows when face-to-face classes will resume. I am just operating under the assumption that they won't. So if I'm proven wrong, hooray! But if I'm proven right, then we'll all be sort of ready to go. Okay, so what are some of the changes that we have to look forward to for the rest of our time together? Well, the first is that our lectures will now be lecture videos. And I will typically try to upload these pretty regularly, usually late in the evenings. And what I want people to think about, or not think about, but to realize, is that right now I'm just using YouTube because I know everybody knows how to access and use or watch YouTube videos. But we might switch to other platforms. So I will let you guys know if we change the sort of software or platform I'm going to use. But for now, I'm going to keep it on a YouTube channel where I know how to link to it and I know you guys know how to watch it with lots of different devices. Another change is to our weekly homework. We will now have weekly homework that's submitted online. And this is going to be through U of H's CASA system. So I'll be sending out more details on exactly how to get that going. Excuse me. Everybody does have access to this, and what you'll notice is I'll start posting assignments there, and I'll also share a document with everybody about the exactly how to upload your assignments. Okay. The other big change, there's sort of two other ones, and unfortunately, I don't really know the answers for what these changes are going to look like. So, first big change that I don't have much clarity on is office hours. So, I will be hosting office hours as regularly as I can, but I don't know what platform is going to be the best way for us to do this. So let me just write down some options for my office hours. I might be using Microsoft Teams. I might use Blackboard. Maybe it would be easier to do some sort of Google Hangout. So the point is, I don't know exactly how we are going to be structuring these. As soon as I determine a best course of action for office hours, I will of course let everybody know. And the last item that I think, oops, what happened there? The last item that's a big change for our class is testing. And just like my office hours change, I have no clear answer on exactly how testing will change. So will we switch to some sort of online test? Or will we just do a sort of open book, open notes test that you submit through CASA? I don't know yet. So unlike some of the other courses that U of H offers through the math department, this course, as you guys know, offers the instructors a bit more autonomy and flexibility to make these decisions. Still, I am required to check with department policy and department administrators to see what options I can give you guys in terms of testing. So look out for information in the coming week or 2 weeks about how we're going to handle this. Okay, so those are all the big changes. Let me remind you, though, of some things that we've been doing for our class that won't change. So things that will stay the same. The first one is our course website. That's going to stay the same. That's where I will repeat announcements and post links now to our lecture videos. This is also where I'm going to keep updating our class notes, so you'll have a written record of what we've been talking about. And then, of course, I'll also be communicating via email, the same way I sometimes do when I need to make an important announcement. So be sure to keep checking all your email and staying on top of all the different changes going on for all of your other courses too. A couple of other things that are going to stay the same is you guys are still going to do great, and we're still going to learn and explore a whole bunch of great math during however the rest of the semester looks. Okay, so the sort of shorthand version of both of these things staying the same is our unofficial class slogan. Yay, math. Alright, so since this is sort of my first pilot video here, let me do an attempt at reviewing some of the important math topics we talked about last time. And that was kind of a while ago, so I'll remind you guys that last time the two main things we talked about were sequences and proofs by induction. And in fact, these two topics go really, really well together. They had a lot of subtopics that you could jot down if you really felt like it. Like sequences, we also talked about series, and a really important subtopic we talked about are recursive sequences, or what you might call recurrence relations. Sort of the same concept with different names. And proofs by induction, there's a whole lot to say about proofs by induction. That's going to be the focus of what I want to review here. All right, so proofs by induction, this is material from section 5.1. And the reason this topic goes so well with sequences is that if we ever want to prove something about a sequence, be it a series or a recursive sequence, oftentimes this new method of proving, this proof by induction, is a great way to go. So let me just sort of remind you some of the key points about a proof by induction. Lots of different analogies sort of suggest what's going on. The analogy we used was knocking over dominoes, and our notes, right, sort of review that proofs by induction are great for verifying formulas. So this is like when you would, as a common situation where you would use a proof by induction. And then you can think about verifying these formulas using these proofs by induction as proving infinitely many statements. So you're proving a statement, it might be like a predicate statement, P0, that's like the zeroth statement. And you might prove the statement P1. And you might want to prove that P2 is true, and P3, and la 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 forever. So to say this without so many dots, we might want to say, proving that for every natural number n, some statement, maybe it's a formula, P of n is true. Okay, and I'll make the sort of necessary fussy little comment about what I've just written here. Of course, you don't actually have to have a statement for every natural number. You might just have a statement for every natural number bigger than 3. Or you might have a statement for every natural number bigger than 1. Sometimes, in other situations, you might have a statement P that is actually makes sense when your variable is -1. So it might be P of -1 is true, and P of 0 is true, and on and on and on. What the most general way to talk about a proof by induction is we're trying to prove an infinite collection of statements, where it's this, by infinite collection, I should really say it's an infinite list of statements. And so there's a first statement we want to prove, and then there's a second one, and a third one, and forever. And so this gets to how the proof works. The two main things you want to think of for how to write a proof by induction is step 1, you always prove what we called the base case. This would be the first statement, the earliest one, maybe P of 0 or P of 1. And then the next step is what we call the inductive step. And that's where we prove an if-then statement. We prove if P is true at some value K, then P is true at the next value, K plus 1. Right, so this is really an if-then. Right, so I'll rewrite it as if P of K is true, then the next statement, P of K plus 1, has to be true. So as we talked about in our last, what might be our actually last in-person meeting, the base case is sort of saying you have one domino that you can knock down. You can flick your finger and knock this domino down. This inductive step is then saying all the other dominoes are lined up, one in front of the other. Right, so this might be the 0th domino, the first one, the second one. And so what this says is, what a proof by induction really is getting at is the following. It says this. It says, if you want to know that P of 1 million is true, you don't need me to plug in 1 million for this variable n and show you that my claim is true then. I can just point out, well, wait a minute. I will show you it's true when n is 0. And then I will show you, as part of my inductive step, that whenever it's true at one stage, it has to be true at the next one. So thinking of this domino analogy, what we're saying is, how do I know the millionth domino will have to fall? Well, I have my first domino that I'm saying I can knock over, and then every other domino after that is lined up in such a way when I knock one over, it causes the next one to fall. Those two pieces are enough for us to conclude that the millionth domino will have to fall. Okay, so our textbook and lots of other online resources and notes have lots of other analogies. I'm actually kind of fond of the domino one, but for right now, you can get a lot out of some of these other analogies that don't use dominoes. There's a staircase analogy, a climbing a ladder analogy. These are all good for right now. But let's do an example. And my example is going to be a little weird seeming. I guess I'll remind you. I'll call this example A. Okay. So my first example A, is going to be about these things that I defined in the previous notes called triangular numbers. And triangular numbers are going to be a sequence of numbers that are defined using a recurrence relation. So I have to tell you what the first couple triangular numbers are. So the first one is just the number 1. And then I have to tell you a recurrence relation so that you can figure out all future numbers. And so the sort of next, the n plus first triangular number is the previous triangular number plus n plus 1. So this is my definition of triangular numbers. It turns out there are other definitions, but we're going to work with this one. That was totally a drink of soda and not vodka, I promise. But you can only see my screen, so you just have to take my word for that. Okay, so one thing I recommend, right, I haven't even finished writing this question, but one thing I recommend is before we get to whatever the question is, let's just try a few examples. You'll see me, I'll try to remember to point this out in all of these induction examples, that whatever sort of formula or thing sequence in this case you're looking at, it's always good to try a few examples to get a feeling for this. So, for example, the first triangular number is 1, but then what's t2? Well, according to my recurrence relation, that should be t1 plus 2. So that should be 1 plus 2. That should be 3. And then what's the third triangular number? Well, that should be 3 plus the previous one. That should be t2 plus 3, which if you work that out, that's 6. And let's just try the fourth one. The fourth triangular number, according to my recurrence relation, that should be the previous triangular number plus the number 4, so that'll be 10. So if I wrote these out in a sequence, it looks like this. The sequence of triangular numbers starts off 1, 3, 6, 10, and then I get to put dot, 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 because we all get to pretend that we're genius jerks, and we say, oh yes, we know all the future terms. And the truth is we don't. We'd have to keep using the recurrence relation to generate them. Okay, so let's get back to the induction part of this example. Here's my induction question. Prove the following. The nth triangular number has this closed form expression. And here's the thing. This doesn't necessarily feel like a claim that's actually infinitely many claims. It just feels like prove that this formula is true. It feels like one single formula. But you want to start training your brain and eyes and ears to understand and see and hear this as infinitely many statements, right? We actually have like the statement P of 1 would be that T1 equals 1 times 1 plus 1 over 2. And that statement P2 would be that T2 is 2 times 2 plus 1 over 2. And that, I'll squeeze it in here before I scroll down, most generally, the nth statement is that the nth triangular number is given by this formula. Right, so this really is infinitely many statements, right? And what really gives you a clue about that is the presence of this variable n. Okay, so let's practice proving this infinite list of statements, this single formula that holds for every n. Let's prove this using induction. Alright, so proof by induction. Okay, so I recommend when you're writing your own proofs by induction, you actually label the steps. So you can put a 1 there and write base case. So when we're doing our base case, what we want to think about is what's the smallest value of this variable, as I've labeled it n, that makes this formula true. And if you think carefully about how I define triangular numbers, I didn't define what T0 means. I started at T1. So for this problem, our base case, we should probably use n equals 1. And so our base case is just checking, is the first triangular number, which I said was 1, does that equal this formula when I plug in 1 for n? And if I work out that right-hand side, I in fact get 2 over 2, which of course simplifies to 1. And so we can say this is true, 1 equals 1. So the formula is true for our first triangular number. Our first domino can be knocked down. And now the magic, the inductive step. This is where we want to show P of k implies P of k plus 1. So here's what we're saying. We're going to say, suppose the formula is true for some value of n, say n equals k. And then in parentheses, I'll say we want to show that it's true when n equals k plus 1. Okay, so this is where all the creativity comes in with a question like this. To get this going, I might say something like, okay, when I said suppose the formula is true for n equals k, I should write down what that means. So this means that the kth triangular number is in fact equal to k times k plus 1, all divided by 2. And what we want to show is that the formula is true for n equals k plus 1, for the next triangular number. So to show that the formula is true for k plus 1, that is, to show that t sub k plus 1 equals k plus 1 times k plus 1 plus 1 all over 2, we first examine t sub k plus 1. So I want to pause here. I'm writing way more words than I would expect you guys to have to write for a proof like this. But again, my words aren't just trying to convey to you that I know how to write the proof. I want to write words that show you how I'm, like, that sort of teach you how I'm piecing the proof together. So the first thing I want to point out is you really want to pause the video and make sure that you understand this right here. This stuff that I just sort of squiggly underlined in pink, this is the formula with n equals k plus 1. And this is almost always a crucial step in your proofs by induction. You need to understand what p sub k plus 1 is even claiming. So you need to be able to take your formula and carefully plug in k plus 1 to see what it's saying should be true. Okay, so, but how do you get that the k plus 1, the k plus first triangular number, is this new red formula? Well, the truth is you don't know how to get it to be true. But you start playing around with, in this case, t sub k plus 1, and say, okay, well, what could happen? What do I know about t sub k plus 1? I don't know much, except this next triangular number is supposed to be the previous triangular number plus k plus 1. How do I know that? That was our definition, our recurrence relation for my triangular numbers. And now I can say, wait a minute. I know that the kth triangular number I get to write as k times k plus 1 all over 2. Why do I get to do that? Because I assumed that formula was true as part of my inductive step. And a great way to write this down when you're writing your own proof is to say, this is by, I'll write it in green to keep color coding it, by our inductive hypothesis. Okay, so what do we have here? Well, we don't have much of anything. We kind of have a mess. we say, okay, we've got the k plus first triangular number over here on the left, and now I've got a bunch of k's, some in green, some in red, and I'm really now just desperately crossing my fingers and hoping that when I mathematically or arithmetically combine all these k's, I get this expression that I'm looking for. I'm trying to see that I get this thing that I'm now squiggly underlining in pink. So will I get that expression? If not, maybe I made a mistake. But if I do get the expression, I kind of will say, oh, thank God, and I wipe the sweat from my face and put a little proof square at the end and act like I knew it was going to work out the whole time. Okay, so let's see if this works out. The first thing I'm going to do is let's switch everything now. Let's uncolor code it back to blue. Okay, so, and then the first math thing I'm going to do is make a common denominator. So that k plus 1 over there, that's really a 2 times k plus 1 all over 2. And then I'm going to, of course, put all of these expressions over that 2. And some of you, probably, maybe many of you, because you're so damn good with thinking about patterns from all of your comp sci training, you may see what's about to happen here. But let me tell you, at this point, that pink squiggly stuff up above, that's what we want to have happen. And we have this blue stuff, and it doesn't quite look the same. At this point, there are a number of approaches to keep taking. And I'll tell you, the first few times I ever did a question like this one in particular, my instinct was, I have all this blue stuff, all this k's, I multiplied everything out, combined a lot of stuff, and then tried to desperately factor it. That will totally work. Let me show you another way that's staring you in the face if you look at this the right way. So what I've got, I'll try and use a highlighter here. What I've got is a giant k plus 1 highlighted in orange, and another k plus 1 highlighted in orange. So what I can do is factor out that entire k plus 1 from both pieces. And what's left over? Well, what's left over, there was a k, and then there was a 2. This is a type of clunky, clumpy factoring that we do tell our algebra students to practice, but it's super easy to forget about it. But notice, right when I write that, this is precisely k plus 1 times k plus 2 all over 2. That's exactly what I wanted t sub k plus 1 to equal. That's exactly what's underlined in pink right up there. And so what you really want to write is, yes, I'm very excited. But what you're actually going to write is a proof square, because your proof is now done. All right, so excuse me, let's just review for a moment. Right? Our base case for this proof about triangular numbers was ridiculously easy to check. Our inductive step took a lot more work, especially if you're playing the role of teacher and explaining where everything's going. And this is entirely typical. Your base case is usually, not always, but it's usually trivially easy to do. It's the inductive step that's easy to get confused with. So just some like last minute pointers about excuse me, about proofs by induction. All right. First one is make the base case as easy as possible. this usually means picking the smallest possible number or value for n that you can plug into the claim or formula. And then for your inductive step, I sort of have two pieces of advice. Write out P of k being true very carefully. You also want to write out the want to show P of k plus 1 very carefully. So carefully plug in k plus 1 into your formula and simplify that expression as much as you can. And then the fourth pointer that I'll include here is the following. Work hard to relate the k plus first statement and the previous statement. This is actually where all the creativity and desperation enters. Sometimes, depending on the nature of these claims, sometimes it's very easy to see how the k plus 1 stage relates to the previous one. But at other times, you don't really know how it works. And so you do what we did in this example. You just keep using what you know. You definitely use your very carefully written inductive hypothesis. You use that wherever you can. Okay, I am going to finish with one more example. I'll go a little bit more quickly through this one. So I guess this will be example B. And this one's going to seem a little bit stranger. It's going to say this. Find and verify, a formula for the sum of the first consecutive, and I'll put in parentheses, positive odd integers. Okay. This example, in my opinion, is a bit more interesting, or if you like, a bit more cruel than other examples. Total non-vodka drink break. Okay. Break over. All right. So this one's a little bit different, maybe a little more cruel, maybe a little more interesting, because unlike my first example, example A, I'm not just saying, here's a formula, use induction to prove that the formula is correct. This is saying, well, first we want you lovely hard-working math cougar, to go find your own formula. And then, so you're going to say, okay, here's the formula I think is true. And then we want you to write a proof. We want you to verify that your formula is true. So, for this part, this is where you're going to use induction in this example. But for the first part, what the hell do you use here? Well, what you use here is, I'll put in quotes, guesswork. That's not exactly what you're going to do. You're not going to just guess a formula. You're going to try lots of examples and then base a guess on the examples that you've worked out. So let's try that. Let's first find a formula for the sum of the first consecutive odd integers. Okay, So here's what I'm going to do. I'm going to say, okay, when we just have one positive odd integer, well, that's just 1. That's the first odd integer. We're not adding any more to it. When we're going to do the first 2 odd integers, we're going to do 1 plus 3, and we get 4. All right. So what if I add the first 3 positive odd integers? Well, that would look like 1 plus 3 plus the next one, which I guess is 5. And if I carefully do that, I get 9. Okay, what if I do the first 4 positive odd integers? That'll be 1 plus 3 plus 5 plus 7, which is 16. Okay. So you might want to pause the video here to see if this is enough for you to guess a pattern that you're noticing here. When I add up 1 odd integer, I get this number. When I add up 2, and then 3, and then 4. If you're not seeing a pattern yet, hit pause and take a few moments to work out the next couple of examples. But assuming you're on board, then you might notice our examples suggest that the answer is always a perfect square, right? It's 1 squared for n equals 1, 2 squared for n equals 2, 3 squared for n equals 3, 4 squared for n equals 4. So it seems like the answer is n squared. And so let me write this as our formula as a sum. It's not tricky or anything, it's just a little annoying to write it out to keep track of where n appears, but let me write it like this. I think j is going to go from 1 up to 2n minus 1. I think, oh, sorry, let me stop that. That's not right. Okay, so we're going to do 2j minus 1. And we're going to go from 1 to n. Sorry, I got a little confused on my indexing. So if you think about what I've written here, that's just a way for me to write, okay, when j is 1, that's 2 minus 1, that's 1. When j is 2, right, the second term in that sum is going to be 4 minus 1, that's 3. So this is really my way of writing 1 plus 3 plus keep going till you get to the nth odd integer. And then you should get n squared. So after some experimenting and desperate searching, here is our conjecture. That the sum, starting from 1 and ending at any number n, of these terms is always n squared. So that, right, that's something you could tell a computer to check by programming this in and saying check that this is true for n all the way up to n equals 1,000,000. But a proof by induction will prove that this is true not just up to n equals 1,000,000, but for every possible value of n. So I'm just going to sort of abbreviate this one, this proof. I'll make it less talky so that I can stop the video soon. All right, so my proof by induction here is going to go like this. Step 1, base case. And for this problem, it wouldn't make sense to plug in n equals 0, but we could plug in n equals 1. And so what we would have here is a sum our index j, starting at 1, ending at 1, of 2j minus 1. So there's really only one term in the sum, and it's just 2 minus 1 equals 1, and that does equal 1 squared. Our formula is true at this base case. And now, again, what I would really encourage you to do is hit pause on this video so that you can try the inductive step. Go make a mess of it. Go get it right. Go get it wrong. We all have our non-vodka drinks to celebrate or commiserate. So it's all good no matter what. But before you watch me spoil this part, try it yourself. Okay, so welcome back. And so here's how I'm going to try to write up our inductive, I said inductive case, our inductive step. I'm going to say, suppose that the formula is true at n equals k. I'm going to say that much shorter. I'm going to say, suppose when I plug in k, so it's going to be j equals 1 all the way up to k of this weird sum, that when I sum up the first k odd integers, I get k squared. And then I can remind myself, we want to show that when I add up the first k plus 1 odd integers, I want to show I get k plus 1 squared. Okay, well, we can rack up a lot of partial credit by saying, well, I'm done, this is as good as I can go, but what I'd like to do instead of stopping here is inch a little bit more forward, because the key thing to remember, our creativity and desperation is now at full peak here. What we want to try and do is relate k plus 1 to k. And this is not always obvious to do, right? So you might want to waste a lot of scratch paper trying things here. But for this problem, I will point out that the sum of the first k plus 1 odd integers is equal to the sum of the first k odd integers plus excuse me, a last term, the k plus 1 term. So this came from when j equaled k plus 1. The whole point of making this observation is this shows me a relationship between the k plus 1th expression and the kth expression. Because now I get to say that this kth expression equals k squared. Why on earth do I get to say that? Well, I get to say that because, and again, I would put this in words in my proof, by our inductive hypothesis, right? We assumed the formula was true when n equals k. And so now we cross our fingers and hope that everything works out. Let's just see if it does. We'll get k squared plus 2k plus 2 minus 1. That's going to leave me with k squared plus 2k plus 1. And if you think about factoring, this indeed equals k plus 1 all squared. So, our conjectured formula is totally correct, right? When we summed up to the k plus 1th positive odd integer, we could use our inductive hypothesis and learn that the k plus 1 sum reduced to or equal to k plus 1 all squared. And that's exactly what we wanted to show. So, rather than writing our celebratory exclamation points, we suppress it, and just write a proof square. Alright everybody, I'm going to stop this video here because I fear it's too long and maybe something's gone wrong in my recording. I will see how this goes, and I hope everybody is doing well, staying safe, and has the luxury of time to think about math, if nothing else, for therapeutic reasons. Alright, love and respect to you guys. I will talk to you soon.